Okay, good morning, everyone. Let's start today's lecture. Okay, today we are going through lecture note number 2. Today's lecture actually covers the first 2 chapters in our textbook. It's all about data. The focus of this course is on analysis. The keyword is large data set. And for different purpose, in different area, the analysis of large data set are for different purpose. For example, industrial process data, the focus would be on optimizing process and improving competitiveness. Or for business data, the focus is on improving cross-selling and customer segmentation. And when we do analysis of large data set, usually we use text and structured data. Basically, it is because our software technique can process such data easily. As you know, there are more and more different types or different categories of data can be used for analysis. If we analyze text and structured data, the analysis result can help to filter, search, extract, and structure information. Image data. The analysis on image data is used for recognize object or classify things. In biomedical data, we analyze biomedical data especially on gene and annotates genome functions. As you know, they try to apply the analysis on biomedical data for the immunity of COVID-19. Okay, then we are going to do a simple comparison on data analytics and data mining. The two technologies both analyze data, but for different purpose. And sometimes they do similar things from the opposite direction. For data analytics, the application, yes? Okay. The application of computer system to analysis of large data set to support decision. So in this category, data analytics, the analysis of that large data set is for the purpose of supporting critical decision, especially in the commercial companies. Usually such decision can make difference of large amount of benefits. So we analyze data to support decision. That's data analytics. Another technology is called data mining. It's a very popular technology we discuss a lot in modern computer science areas. For data mining, the purpose is to extract knowledge from data. The special thing is usually when we do data mining, there is no specific goal. How many, for example, how many categories we are going to classify the data. But we apply data mining algorithms on the data. This data set will get different number of category by applying the same algorithm. So it depends on the distribution of the data in the data set. The key point is that when we apply data mining technologies, usually we don't have some specific expected pattern that we may find in the data by a certain algorithm. We will let the data speak for itself. Different data set will come out with different conclusion. That's the interesting part of data mining. So when I say data analytics and data mining might come from the opposite direction, is that for data analytics, we usually have a specific goal, but we need to accumulate enough evidence to support the decision to be made. However, for data mining, usually we don't have a specific goal in mind. We will let the data speak for itself, and we wait and see how this set of data come up with some kind of pattern. So that's usually they apply similar technology or similar technique algorithms, but we do these two things from different directions. In this course, of course, we emphasize on the part of data analytics instead of data mining. Data analytics is a very interdisciplinary field. The authors of our textbook mentioned 7, 6, 8, uh, six different areas as the interdisciplinary field required by the engineers in for data analytics. First one is statistics. So you will see a lot of scholars from statistic department in colleges go to the same international conference with me. There are a lot of statistics person working on data analytics, machine learning. Uh, there are in a lot of cases, we will apply machine learning algorithm to construct the data analysis engine. They can do automatic analysis or automatic updates when new data comes in. Pattern recognition. As I said, data analytics is majorly for supporting decision. And usually when we make decision, we want to identify the pattern of new things or new evidence or new trends so that we can make correct decisions. So it's very important to recognize the patterns in data. And system theory, operation research, and also artificial intelligence are the related area of, or when we do data analytics, we might require your knowledge in such areas. The phases of data analysis project. Usually data analysis project apply this 4-phase strategy to execute or to realize their project. The first phase is data preparation. Since we are going to analyze data, the first thing is that we need to get the data and do some preparation work made to exclude so-called noisy data or irregular data. And if the data format does not follow our expectation, then we need to transform the data a little bit so that we can do the analysis following. That's data preparation is for planning data collection. But what I said, some of what I said is actually in the category, in the phase of pre-processing. Pre-processing includes cleaning, data cleaning. When I say noisy data or irregular data should be excluded, it's data cleaning. Filtering. Usually we will get a very large data set for analysis, but certain analysis only needs part of the data collected. So we need to filtering out those data not of our interest, not of our interest for this analysis. Completion. Sometimes we will get some incomplete data set. So we need to set up the rule when certain data is incomplete, what do we need to do? Do we want to analyze the data based on the incomplete data set, or do we want to ignore those incomplete data sets? That's two of the most popular strategy when we find incomplete data in the large data set. Correction. Some obvious errors in data may be corrected in this phase. And standardization. Because we are analyzing large set of data and the source of data may be different, or I should say the data may be collected from various data sources. The data from different sources might apply different scale. For example, if you for the data of weight, in some country they used to store weight data in the unit of kilogram, and the other might use pound. Then we need to standardization or transformation them into a unified scale. The surface is the focus of the data analysis project. The analysis algorithm is applied here in the third phase. We may use the techniques in visualization, correlation, regression, forecasting, classification, and filtering to do the analysis. And since all the simple or naive analysis has been done in this area, now we see a lot of new analysis requires the algorithm from multiple, two or more in this 7 category, from visualization to clustering. It's possible that if you want to do certain kind of analysis, you need to apply the algorithms in more than one categories. Post-processing. After the analysis, there are some work still need to be done after the analysis. For example, interpretation of the data and documentation on what's going on in this project, and evaluate successful or failure for this analysis. Okay, that's the first part. Any questions? Any question? What I'm doing is do a tiny break here because am I going too fast? We already go through 1/3 of the lecture notes. Any question? If no question, then I'm going to move on.
No, Prof.
Okay. Okay. The second topic of today's lecture is for the iris data set. And the iris here is not a name of a person. It's this flower. I searched the internet and get a photo of iris flower. The iris data set is a famous or popular data set uh, which was originally created in 1935 by American botanist Edgar Anderson, who examined the geographic distribution of iris flower on the Gaspé Peninsula in Quebec, Canada. So the data was collected in Canada. So in the beginning, it's just a record kept by Edgar Anderson. It gets popular later on. For example, in year 1936, Sir Ronald Eimer Fisher used Anderson's iris dataset as an example of multivariate discriminant analysis. It is a kind of analysis applied in statistics. So he used this data set as an example to show the techniques for multivariate discriminant analysis. And subsequently, the iris dataset became one of the most frequently used reference dataset in statistics and data analysis. So we are going to take a close look at them. Okay, these are part of the iris dataset. Here we show the three different species of iris flower: Setosa versicolor virginix. And we keep the measure in sepal and petal. Sepal is the looks like the green part, right? Looks like the leaf just below the flower. And petal is the pieces constitute the flower. So when he saw a iris flower, he measured the width and length of sickle and width and length of petal of these three kinds of iris flower. Okay, the textbook gives us some typical questions of data analysis on the iris data set. They did not give the correct or uh, direct solution to these questions. So I will view these questions as open questions. you may think about it. Which of the data might contain errors or false class assignment? So you went through the data. Is there any irregular data? Usually, you look at the largest number and smallest number is far different from the other data. For example, for the data on the right hand side, because the figure is larger, you can read the numbers. The smaller the figure on the left hand side, it is a little bit small, but you can see the figure in textbook. Okay, let's look at the right hand side and try to find the irregular data on the fourth column, the width of petal of setosa. I found one, 0.6. Everything in this column is between 0.1 to 0.4 and only 1.6 there. So it's a little bit far away. The difference to the other data is a little bit large. So this might be the error data. Which is the error caused by rounding data off to 1 decimal place? As you can see, these data are numbers rounded to the first place after the decimal point. And once again, the fourth column, the width of petal for setosa, the number, the value of the number lies in between 0.1 to 0.6, especially for those data of 0.1 and 0.2. The second place after decimal point might be critical. For example, if it is shown as 0.1, the possible value for that is 0.5 to 0.14, right? So if two rows of that column are both 0.1, but the actual data might be very different. For example, one of them is 0.05 and the other is 0.14. It's almost 3 times as large as the other. So that's a problem happens in rounding the data off to the 1 decimal place. What is the correlation between petal width and petal length? Well, you look at data by yourself and see if you can come up with any observation. Okay, I'll let yourself to do it. Which pair of dimension is correlated the most? To me, for example, the length of sepal of vernicolor, versicolor, and the column for length of sepal of virginica. The fifth column and the ninth column, the fifth column and the ninth column, it seems that the ranges of data are similar. Okay. The next, none of the flowers in the data set has sepal width of 1.8 centimeter. Which sepal length we expect for a flower that D have 1.8 centimeter as its sepal width? Let's look at sepal width. All the sepal width are larger than 1.8. The closest, the nearest value is 2.3, right? 2.3 is the second row of sepal width of versicolor. Yeah, we are looking at sepal width. The second row on the sixth column, it is the nearest number to 1.8, which is 2.3. So I would expect if we do have the data 1.6 as sepal width, maybe it's versicolor. Okay, which species will an iris with a sepal width of 1.8 centimeter belongs to? Yeah, I just did that. Do the three species contain subspecies that can be identified from the data? I believe so, but since I only look at the right hand side, if you, I could not tell yet. If you look at the total, the whole data set, maybe you can observe the answer to this question. Okay, these are some typical questions for the iris data set. Okay, when we talk about data analysis, we start with the discussion in data scales. Actually, in our textbook, when we say data scales, we actually classify the data, the numerical data, into four kinds. As you can see, there are 4 rows in the table on the right. Right, let's look at the lecture notes. Numerical measures may have different semantic meaning, even if they are represented by the same numerical data. For example, 1.8 for some column may be a very large number, but 1.8 for the other column may be a very small number. Depending on the semantic meaning, different types of mathematical operation are appropriate. Let's look at the 4 scale. The summary is on this table. The description is here. The first type of data is called nominal. Nominal scaled data is used for tests of equality or inequality only. So we don't do mathematical computations on the data. We just compare them. Are they equal or not? If the data is used only for comparison, of equality, it is called nominal data, nominal scaled data. The feature of this data scale is mode, the value that occurs most frequently in the nominal scale data. Okay, the second types of the data is called ordinal. Ordinal scale data, for ordinal scale data, we may apply operations like greater than and less than. We may compare which one is larger, greater than the other. If you compare ordinal data with nominal data, we never compare what's the greatest data in nominal data. We only compare for equality in nominal data. However, in ordinal data, not only we can compare for equality, but we can apply greater than and less than test. The feature of ordinal data is something like median. Median is the number in this set, and there are as many smaller number than median as the same as many number of larger values in the set. For example, if we have 99 numbers in the set, the median is the value of 50th largest or 50th smallest, the middle one. If you sort, since we can compare greater than and less than, we can do sorting. If we sort the data set, the middle, the number at the middle position of the array is median. The median number may be different from means or average, which is the feature of the third type. The third type is called interval scaled data. For interval scale data, not only we can test for equality, test for greater than, but also we may apply addition or subtraction. The feature number is mean, is in general sense, it's the average value. If we are going to compute means, we need to do addition. We need to do addition on all the data value and multiply by the number of data we have. So addition, if we want to compute means, it means that the data can be added. As you can see, the first two types of data, we cannot add them. So the feature mean is actually what we usually call it the average value. Okay, the last type of data is ratio scaled data. For ratio scale data, not only we can do test for equality, test for greater than, and addition, but also we can do multiplication and division. So for ratio scale data, we can use generalized mean as a feature. And generalized mean, the formula to compute generalized mean is a small figure I included in this page. Alpha could be any number, for example, 2 or -1. If it's 2, then we summation on the square of the data, and we divide it by the number of data we have, and we do a square root computation. Then we get generalized mean when alpha is 2. But the key point is that if this data may be multiplied with each other, then it's ratio scale data. If the data in this set may be added together, then it's interval scale data. For ordinal data, we can compare greater than or less than. For nominal data, we can only test for equality. Set and metric representation of numerical data. If we collect the numerical feature data of certain item, we can show the data we collected as a one-dimensional array like this. X, the data for X are x1 to xn, small x1 to small xn. And if we collect a larger set of X, then we extend the idea to a two-dimensional array, as shown in the small figure on the left. So numerical feature data are also often represented as a matrix, just a general form is shown on the left. Considering a matrix, especially the numerical data set in a matrix, each row corresponds to one element of data set, and each column corresponds to one component of all elements of the data set. And usually a number in the matrix is denoted by xk of I. The subscript k means the position in the matrix is the kth row. The I on the top right corner is means that the data is at the ith column of the matrix. So we use this to denote the position of the data in the matrix. The iris data set is just a simple data set with 150 rows and 4 columns. Whoops. When I see this in textbook, I wonder, oh yeah, because I see the picture, in the figure, we have 12 colors, but that's 4 different kinds of iris flower. For one kind of the iris flower, we have 4 colors. Okay, it's not so big, not a big data set. It's just a data with 150 rows. It's quite small from the viewpoint of big data. Okay, relations. Consider a set of elements without referring to numerical feature vectors. We use a big O for the set. of element without numerical feature vectors. The elements are numbered as small o1 to small o(n). The relation of all pairs of objects can often be quantified and written as a square matrix, as you can see on the right. That's the relation of all pairs of the object. The first one, the first data, the relation of between first data and itself is R11, and so on. So each relation value Rij, I and j are both between 1 to n, may refer to a degree of similarity, dissimilarity, compatibility, incompatibility, proximity, or distance between the pair of objects from OI to OJ. And it depends on definition of the value we showed here. The relation from OI to OJ may be different from OJ to OI. It's possible. But but in most of the case, they are the same. For example, the distance from OI to OJ is exactly the distance from OJ to OI. But they may be different. But although most of the cases they are the same. Okay, that's the second part. I have worry about, am I going too fast? Are you, can you follow my pace? Okay, since we are going very fast, do we need to take a 10 minutes break here? Or do you want me to move on? If I move on, I'm going to finish all the lecture notes. Anyone? Okay, those who want to take a break, use the raise hand function of this system. Let me see if some of you raise your hand. Okay, let's take a break. Okay, come back at 10 after 10. Okay, let's take a 15-minute break. Okay, before we continue, just to remind you that you can do the quiz now if you would like to. The link for uploading your quiz number 1 is already open, so you may start doing the quiz at the same time. Okay, let's go back to our lecture notes. Data measures. Okay, here we have we talk about similarity and dissimilarity. When we say dissimilarity, sometimes we use the distance measure to show the dissimilarity. Okay, the distance from x to y is denoted as d parenthesis x comma y parenthesis. It equal to d parenthesis y comma x parenthesis. That's formula 2.7. Okay, if the distance between between x and y is 0, then x equals to y. The point goes to itself, its distance 0. So if it goes, x goes to y with distance 0, then x is equal to y. Okay, formula 2.9. Distance between x and z is less than or equal to distance between x and y plus distance of y and z. That's if y is in the line between x from x to z. If y is located on the line from x to z, then the formula is equal. Distance from x to z is the same from as distance from x to y plus distance from y to z. If y is not on the line from x to z, then the formula is less than the distance from x to z is less than the distance from x to y plus distance from y to z, because these 3 points forms a triangle, right? The summation of the two sides is larger than, strictly larger than, greater than the length of the third side. Okay, for any 2 points, x and y, the distance from x to y is greater than or equal to 0. So that's the distance measure. We usually to use this measure to show the dissimilarity. And there are a lot of more complex measures. I just show some of them discussed in our textbook. The formula 2.16, x of a is the square root xaxt. That's called matrix known. X and transpose of x, and there is an a in the middle, and we take the square root. And Euclidean norm is that every data is related to itself and not related to the others. So you can see the line from top left corner to bottom right corner. All the numbers in this line is 1, and the other numbers are 0. That's Euclidean norm. Hilbert's-Smith norm. All the numbers in the matrix is 1. And diagonal norm. It's similar to Euclidean norm, except that the number at the diagonal line are numbers which might be not 1, other than 1. And they give the number from D1 to DP. All the other numbers not in this diagonal line is 0. It's called diagonal norm. So it's a variation of Euclidean norm. Similarity measures. We show the dissimilarity measure as distance measure. Now we show the similarity measures. A function S is called as similarity or proximity measure if for all x and y in RP, 3 formulas. I show the 3 formula on the right. Either S x to y equal to S y to x, or S x to y is less than or equal to S x to x, and S x to y is greater than or equal to 0. All 3 formula holds. Then this function S is called similarity function or similarity measure. If a function satisfies these 3 conditions, it's similarity measure. The function S is called normalized similarity measure if additionally S x to x is 1. So normalized similarity measure For a function to be called as normalized similarity measures, it must satisfy 4 formulas, the 3 on the top right corner, and additionally, s from x to x is 1. Any dissimilarity measure D can be used to define a corresponding similarity measure S or vice versa. In other words, we can also define a similarity measure S based on D. The formula is shown on the right. S from x to y equal to 1 over 1 plus dx to y. So that's the similarity function defined by this similarity measure D. Okay, edit distance. Sometimes it is called as Levenshtein distance. Usually you just call it edit distance. The edit distance from I to j is I if j equal to 0, or it is j if I equal to 0. If otherwise, we use this minimal formula to compute the edit distance. And we can write a program based on the formula 2.39. That's the algorithm for the program computing formula 2.39. Well, when you look at the definition, it is a little bit difficult to understand, but when you look at the example, it's easy. We need to compute the edit distance from Caesar to Cleopatra, the emperor of Rome and the queen of Egypt, right? Okay, we list the character in Caesar vertically as the first column, and we list the characters in Cleopatra horizontally as the first row, and we leave the first row and first column as blank. Okay, for example, we start from the 0 at the top left corner. If we go to the right, it compares space and C. If they are different, then we plus 0 by 1, so it's 1. And L and compare L and space, it's different, so we add 1 by 1, it's 2, and so on. So if they are the same, then we don't add number. For example, if we go to the cross as C and C, it's the same character. So we take the value from the top left corner, which is 0. So we don't add any value to the 0. And so on. And if you complete the computation of this two-dimensional array, you will get the edit distance of these two strings as 5, which is shown at the bottom right corner. Okay, there is another way to compute edit distance, showing the figure on the right. You list the spelling of Caesar as the first row and show the spelling of characters in Cleopatra as the third row. We do the computation in the second row. We try to match the same character as many as possible. So we can see there are both C in the strings and E also in both strings, and the A is both in the both string, and R also in both string. So we line them up at the same color. So C to C as the first column, E to E as the third column, A to A as the sixth column, R and R are at the eighth column. So we go from left to right. If they are the same, it's 0. If they are different, we add 0 by 1, it's 1. No, we don't do addition. C and C are the same, so it's 0 in the second row. A and L are different, so it's 1 in the second row. E and E, the same, it's 0. S and O is 1. Space and P is 1. A and A is 0. Space and T is 1. R and R is 0. A, space and A is 1. And we count how many ones in the second row. That's 5. So this computation is the for computing edit distance. For those who are interested in the detailed definition of formula 2.39, you may try to compare these two kinds of computation and what's in the formula. Okay, let me do a preview. Our quiz is for computing the edit distance between sitting and kitten. So if you would like, you can do it now as I go to the final 2 slides in lecture notes. We can do the numerical data representation for continuous signal. The technique used is called sampling. The original signal is on the left figure, and we can measure the value of in a fixed time interval. So the value we measured are shown in the figure on the right. That's called sampling. And the way we do sampling, when we do the sampling periods is critical. As you can see, this figure shows 3 kinds of sampling periods, and they result in a very different shape of figures. So when we do sampling, we need to take care of choosing the number or choosing the time length for periods. Okay, that's all I would like to talk about in this lecture. This lecture actually covers the first 2 chapters in our textbook. Oops. Oh, yeah. So the quiz number 1 exercise. What is the edit distance between sitting and kitten? And you may refer to slide 21 of this lecture notes. The way we do the quiz is like this. You may either write on a paper and take a photo in JPEG format, or you may type your answer with Word and save as a PDF file. The key point is you upload only one file for a quiz exercise and try to use JPEG format or PDF format when possible. Because I don't want to see something like 50 different types of files in your uploads. Okay, in case you absolutely need multiple files to complete the exercise, do a zip before you upload, zip or RAR before you upload, so you can upload one file only. Okay, the regular due for this exercise is 12 o'clock today, the noon. If you can upload the quiz exercise before noon, there is no penalty for quiz 1. Late due, we only accept late handing before October 8th, 12 o'clock. That's 1 week. We only allow 1 week lateness. But if you're sending the exercise in the late due, there will be a 10% penalty. Basically, I don't want you to handing after the late due, but if you insist, I will take it, but with 50% penalty if you handing after the late due. Okay, do this exercise, and if you upload your answer, then that's it. That's it for today.
Professor,
Yes.
can you go back to slide 21, please?
Can you download the lecture notes and do it there?
Because I cannot.
Oh.
I cannot. I cannot.
Okay, but I would like to take the question from 嘉伟。嘉伟有事吗？在看到你举手。
老师
Yes.
那个在医学院上面没有上传的案件。
没有？
对。
有啊，在第2周 Quiz 1那边啊。
可是里面不能上传东西。
为什么？
因为它有案件。
有啊，我都点进去了。
其实那个在我这边显示的是像已经过期了。
过期？
它没有按键可以按。
不，你游标到 Quiz 1，它就会变成一个手指一样的小 icon， 就可以点下去了。
点下去，可是里面只有 available from 还有 due date， 没有按键。
人家在右上角有一个更新作业。
更新吗？更新了也一样。
这个是我，奇怪，等一下，等我看一下。可是已经有11位同学上传了。
应该是我的医学院有问题。我知道了，我还没登入，不好意思。
OK，
谢谢。
Any other questions? Okay, I'm going back to the lecture notes.
Professor,
Yes.
where can I submit the quiz? Because I out of list now.
Okay. You got messenger. Are you the one in the list for extra Cs? What's your name?
Vacharapon, Professor.
Don't send it to me. Send it to TA.
Uh,
Okay. Because we are going to grade the quiz by the other TA. So, okay, send it to me.
okay. Via messenger.
Yeah.
Okay. Thank you, Professor.
All right.
Professor, I could put my email so they could send it to me.
Sorry, you want me to add you?
No, it's free, man. I'm saying I'm here in the channel, so I could put my my email address and they could send it to me.
Oh, okay. I see what you mean. Okay, I'm going to do that. But first, let me show the quiz. Someone want to see the quiz question?
Okay.
Let me finish this first, and then I will post your email. This one? Yeah. Okay.
Professor, it's not.
Yeah.
It's not this slide, Professor.
Not this one. You want this one?
The example of
This one?
this. No,
Okay.
20. Yes. Okay, thank you, Professor.
Excuse me, Professor.
Yes.
Because system dropped this course for me, but you will give me QR code later. But how can I upload the quiz if I don't have access to e-learning?
Okay. Oh. Huh? Okay, let me do this. Wait a second. I'm going to.
Or what about what I just sent?
I will post the email address of TA and you send it to him.
Okay, I
by
sent it.
email.
Okay. Thank you. Or I can send to the messenger, or just.
Yeah, if you have my messenger, yeah, you
Okay,
may send it to me.
Okay, I will send to you quiz. Thank you.
Okay. keywords.